Close your eyes and imagine yourself floating far above the Earth, not just a few kilometers above the clouds, not even in the silent domain of satellites, but so far out that the whole planet is a small blue marble, spinning gently against a dark velvet sea. The air is gone here, replaced by pure emptiness, and the only thing between you and infinity is the faint shimmer of starlight. There is no sound, no wind, only the hum of your own breathing, steady, calm, and slow. The universe stretches in all directions, without edge or wall. Yet, strangely, it is not infinite in what we can reach or know. There is an invisible horizon, a boundary not made of walls, but of time itself. This horizon is set by a number 299,790 kilometers per second, the speed of light. At first, it sounds like just a fact from a textbook, a speed so fast that nothing in your daily life compares. But here, floating in the vastness, you can feel what it means. This is not just speed. It is the cosmic tempo, the rhythm that space and time themselves keep. It is the invisible thread that weaves the universe together, ensuring that everything unfolds in the right order. Imagine dropping a pebble into a perfectly still lake. Ripples spread outward, gentle and precise. They move at a fixed pace, never rushing ahead or lagging behind. Light is like those ripples, but on the grandest scale imaginable. No signal, no influence, no whisper can travel faster than its wave. This limit defines the shape of reality. It tells us which events can touch each other and which will remain forever isolated. Beyond 13.8 billion light-years away lies a horizon we cannot cross, not because there is nothing beyond, but because light from there has not yet reached us. The early universe still hides behind that curtain, waiting for its photons to arrive, and yet, some of those ancient messengers have made it here. They left their birthplace 13.8 billion years ago, when the universe was only 380,000 years old, when matter and energy finally cooled enough for light to travel freely for the first time. This first light is still with us now, stretched into microwaves by the expansion of space. If you could tune your senses like a radio, you could hear its faint hiss. Astronomers call it the cosmic microwave background. I like to call it the afterglow of creation, the oldest photograph ever taken, printed not on paper, but on the sky itself. This light seeded everything that would come later. Galaxies spinning gracefully, stars igniting, planets forming, oceans filling, life breathing, and all of it has been shaped by that same cosmic speed limit. If light could go faster, the universe's story would be different, chaotic, perhaps even impossible. But here, in this quiet vastness, the rule holds. It is a constant, a promise, a kind of mercy. Now let yourself drift downward, through the black expanse, past the silver dust of the Milky Way, past our sun, a glowing coin of fire, down toward the pale blue earth. The atmosphere catches the light, scattering blues, softening shadows. You fall gently through clouds until you stand once again on solid ground, among the familiar. But even here, in the ordinary world, the rule of light quietly shapes your life. You check your phone's map, and your location appears with precision. This is thanks to a constellation of GPS satellites, each orbiting far above, where gravity's pull is weaker and time ticks slightly faster than it does here on the ground. Their motion slows time a little too, in the opposite direction. Both effects, gravitational and speed-based time dilation, must be accounted for with mind-bending accuracy. If engineers ignored Einstein's relativity, your position would drift by kilometers in minutes, but they don't. They keep the clocks in sync, and the satellites whisper your coordinates to your device, all at the speed of light. You board an airplane and rise into the sky. High above the earth, your clock ticks a tiny fraction faster than someone standing by the sea. An astronaut in orbit will return home a few microseconds younger than if they had stayed on Earth. The effect is small, invisible in everyday life, but it is real. Even within your own body, the top of your head ages ever so slightly faster than the soles of your feet. Light and the way it sets the stage for time makes these delicate differences possible. And then there is the way light touches you directly. It filters through your curtains in the morning, scattering into soft gold. It warms your skin, stirs your mind awake, paints the room in colors. It moves across the sky as the day unfolds, turning amber in the evening before sinking away into night. These photons are more than brightness, they are history. They were born in the heart of the sun, in nuclear fusion reactions that transformed hydrogen into helium, releasing energy that began as gamma rays. For thousands, even millions of years, they bounced within the sun's dense interior before finally escaping into space. Only then did they race to Earth in just over 8 minutes to land gently on your face. Every meal you eat is also touched by sunlight. Plants capture photons in photosynthesis, turning light into chemical energy, stored in sugars. Those sugars become the foundation of the food chain, feeding you whether you eat fruit, grain, or the animals that ate the plants. In a sense, you are made of sunlight, shaped by it at every level from the cells in your body to the memories in your mind. Breathe slowly. Imagine yourself glowing faintly in the dark, because you do. Your body radiates warmth in the infrared spectrum, invisible to your eyes but obvious to any thermal camera. You are like a quiet star, giving back to the universe the energy it has given you, and somewhere out there, that warmth will drift forever, fading into the background, joining the great ocean of light that fills all space. Now, let's shrink even smaller, leaving behind the human scale, diving down into the quantum world, where light reveals its strangest secrets. Here, photons are not just waves, or thus particles, they are both, and neither, depending on how you look at them. They carry no mass, yet they have momentum. They always move at the same speed in a vacuum, no more, no less. They do not slow with age, nor do they rest. If you could somehow ride alongside a photon, time itself would freeze from your perspective. The journey from a distant star to your eye would be instantaneous for the photon, though millions of years for you. Your eyes are sensitive quantum detectors. They absorb photons, translating their frequencies into the colors you see. High-frequency photons appear blue or violet, low-frequency ones, red or orange. This color is not really in the light, it is your brain's interpretation of the photon's energy. At the deepest level, reality is made not of colors but of vibrations and probabilities. Scientists have long puzzled over this duality. In the famous double-slit experiment, single photons sent toward to narrow openings create an interference pattern, as though each one behaves like a wave exploring all possible paths. But if you place a detector to see which slit the photon goes through, the interference vanishes. The act of observing forces the photon to choose a path, collapsing its wave function into a single outcome. It is as if light waits for your attention before deciding how to behave. Even in darkness, the dance continues. Plants use photons with exquisite efficiency, routing them through molecular pathways in ways that still inspire human technology. Your brain, too, hums with electromagnetic rhythms, waves of electric potential that carry thoughts and feelings. Light is not just out there, it is within you, woven into your biology and your consciousness. Beyond what your eyes can see, there is more light: infrared warmth from living bodies, ultraviolet from the sun that tans your skin, radio waves carrying voices and music through walls, microwaves cooking food, X-rays peering through flesh to bone. All of these are light, differing only in wavelength and frequency. The visible spectrum, the rainbow is just a thin slice of the full symphony. And so, as you sit or lie here, listening, perhaps on the edge of sleep, remember, you are already part of light's story. You are made of atoms forged in stars, illuminated by photons that have traveled across impossible distances to find you. You are, in a quiet way, a being of light yourself. From the quiet shimmer of the quantum realm, let us drift back outward not to the vastness of galaxies just yet, but into the hidden fabric that connects them, space-time itself. Here, light is not just a traveler, it is the law that every traveler must obey. Its speed is constant for everyone, no matter how they move. And because of this, space and time must bend, stretch, and warp to keep that promise. Imagine two people holding stopwatches. One stands still, the other rushes forward at an incredible speed. In the world before Einstein, you might think they could simply compare the seconds on their watches when they meet again, and both would match. But in our real universe, the moving person's clock will tick more slowly, not because the mechanism has changed, but because time itself has flowed differently for them. This bending of time is not a rare trick, it happens every moment. High in the mountains, far from Earth's center, the pull of gravity is weaker, and clocks tick ever so slightly faster than they do at sea level. In deep valleys, time is a fraction slower. The difference is too small to feel, but not too small to measure. Physicists have seen it in experiments, confirming what Einstein's equations predicted. And then there is mass. The more speed you gain, the more energy it takes to keep accelerating. Your mass, from the point of view of an outside observer, swells not because you are gaining matter, but because energy and mass are two faces of the same coin. E equals mc squared. This is not just a formula. It is the key to why nothing with mass can ever reach the speed of light. To accelerate to that pace would require infinite energy, an impossible demand. For light itself, this is no problem. It has no mass, so it does not need to spend energy on acceleration. It simply exists at its constant speed, from the moment it is born until the moment it is absorbed, and in its own frame of reference, if such a thing can even be imagined. Time does not pass. A photon leaving the sun and striking your eye 8 minutes later would experience that journey as no time at all. Gravity, too, is part of this tapestry. In Einstein's view, gravity is not a force pulling on objects from a distance, but the curve of space-time itself. Mass tells space-time how to bend. Space-time tells mass how to move. Planets orbit stars not because they are pulled by invisible strings, but because they follow the curved paths carved into the fabric of the cosmos. Light follows those curves as well. Near massive objects, like the sun, light's path bends. This is not because the sun grabs the light, but because the space it travels through is warped. In distant galaxies, the effect can be so strong that light from even more distant sources is bent into arcs and rings, Einstein rings, frozen, halos of light that reveal the hidden presence of matter we cannot see. And then there are black holes, the most extreme curves of spacetime. Here, the warping becomes so intense that beyond a certain boundary, the event horizon, not even light can escape. From outside, nothing within can send a signal out. Yet the edge itself can shine, as matter falling inward heats to incandescent temperatures, releasing its final light before crossing the horizon. In some cases, light can orbit a black hole at a perfect balance, trapped in a circle until it is scattered away or swallowed. All of this slowing clocks, growing mass, bending paths is bound by the same cosmic speed limit. But what if you could chase light? What if you could build a ship faster than any made before, and pour energy into it until you were nearly as quick as a photon? You would find strange things happening. As you draw closer to light speed, time aboard your ship would slow to a crawl. Relative to those you left behind, a year's voyage for you might mean decades, centuries, or even millennia passing back home. Your destination, though many light years away, would seem to rush toward you, the distance shrinking as space itself contracts in your direction of travel. Yet no matter how close you get, the beam of light ahead of you would still recede at the same speed. The universe keeps this rule without exception. If you could somehow overtake light, the rules of cause and effect could unravel. Effects might precede causes. Messages could be sent to the past. Paradoxes would bloom, situations in which reality contradicts itself. Physicists have imagined hypothetical particles called tokens, which would always travel faster than light. In equations, they exist, but in reality, they remain ghosts, mathematical warnings that perhaps such speeds are not meant to be. There is one place where faster than light motion seems to occur, but it does not break the rule: the expansion of the universe itself. Space can stretch so quickly that distant galaxies recede from us faster than light, not because they are moving through space that fast, but because the space between us grows. Light from those galaxies will never reach us, not because it is slow, but because the road is lengthening faster than the traveler can run. Still, in our local patch of the cosmos, light remains supreme. It guards causality, the sequence of events that allows meaning to exist. Without this limit, the story of the universe would not be a story at all, but a chaotic blur without before or after. Think for a moment about light's journey from a star. Deep in the star's core, photons are born in fusion reactions. But they do not stream outward immediately. Instead, they bounce from particle to particle in a dense plasma, taking thousands, even millions of years to finally escape into space. Once free, they fly straight and steady, perhaps toward nothing in particular, perhaps toward a planet like ours. They may travel for billions of years, crossing gulfs where no planets or dust clouds interrupt them. And yet, when they finally meet your eye, the image they carry is a record of the past. Every time you look at the night sky, you are looking backward in time. The light from the moon is a little more than a second old, from the sun, 8 minutes, from the nearest star beyond the sun, more than 4 years. From some galaxies, millions or billions of years. The photons you see tonight may have begun their journey before humanity existed, before Earth was as it is now. Some of the stars you see may already be gone, their light still en route, the final message of their long lives still crossing the darkness. In this way, light connects us not just to distance, but to time itself. It is a bridge across the ages, allowing you to see what was, even if what is has changed. And even here on Earth, nothing is truly instantaneous. The signals in your nerves travel at about 100 meters per second, not nearly as fast as light. When you feel the warmth of the sun, that heat is the end of a journey that began millions of years ago inside a star. When you look at a loved one's face, the light reaching your eyes left them a fraction of a microsecond earlier. You are always seeing the world as it was, never as it is. Far from being a flaw, this delay is part of the rhythm of existence. It gives the universe a tempo, a pulse. Your heart beats, your breath rises and falls. The seasons turn, all because time unfolds, and light sets the pace. You yourself are part of this cycle. The atoms in your body were forged in stars long gone, scattered into space by supernova explosions, gathered into clouds that formed new suns and planets. Some of those atoms have been part of countless other beings, plants, animals, perhaps even other people before finding their way to you. You are a chapter in their journey, and one day they will move on again, and through it all, light moves to carrying information, energy, and memory. It bends around masses, it reflects from surfaces, it is absorbed and re-emitted. In this way, light is both the messenger and the message. So, as you drift deeper into this quiet understanding, let yourself imagine you are not separate from the cosmos. You are made of its dust, warmed by its fire, illuminated by its photons. You are a participant in the great conversation between matter and light, energy and time. And the speed limit that governs all things is not a barrier meant to hold you back. It is the very structure that allows you to exist, to think, to wonder. And now, let us walk together toward the edge of imagination, to the place where science meets philosophy. The speed of light minus 299,790 kilometers per second is not just a number on paper. It is a kind of poetry written into the structure of the universe, a silent agreement between space and time. Like the rhythm of a song, it sets the pace of every story ever told, From the birth of galaxies to the beating of your heart, if there were no limit, imagine how different existence might be. Information could arrive before it was sent. Effects could ripple backward into causes. The delicate unfolding of events, the very idea of a beginning and an end, could dissolve into chaos. A sunrise might happen before the night has fallen. A question could be answered before it is asked. In such a world, meaning itself would be fragile, perhaps impossible. There would be no pauses for thought, no anticipation, no suspense in the turning of a page or the waiting for a reply. Everything would collide into a single, incomprehensible instant, but the universe chose otherwise. It chose a tempo. It chose a heartbeat slow enough for stars to form, for planets to cool, for oceans to gather, for life to emerge, and for minds to wonder about it all. This limit is not a prison wall, it is a womb. Without it, there would be no space in which to grow, no time in which to dream. Think of your own life. The moments you cherish most are not instantaneous, they unfold. The smile of a friend is not simply there all at once, it blooms in the space between seconds. A song builds its beauty not from a single note, but from the way each note follows the last, at a pace the ear can savor. Even love itself grows over time, weaving memories, glances, and shared silences into something greater than any one moment could contain. The speed of light grants the universe the gift of pace, and with it, the possibility of story. Light, in all its forms, is a patient traveler. A photon from a distant galaxy does not rush. It simply moves at the only speed it can, carrying with it the memory of where it has been. When it finally reaches you, perhaps after billions of years, it is offering a message from the deep past, a cosmic postcard saying, "I was here, long ago, and now I am with you," and we, in return, are constantly sending our own messages into the cosmos. Every broadcast, every radio wave, every flicker of light from our cities races outward at light speed, spreading our presence into the galaxy. Long after our words have faded here, they will continue their journey among the stars, perhaps to be found by other eyes, other minds, in some far-off future. Consider the strange symmetry of it. Light does not age, yet it allows aging to happen. It moves outside of time, yet it defines time for everything else. From its point of view, a journey of 1,000,000,000,000 years is the same as a blink. And yet, because we are not photons, we feel every heartbeat along the way. This difference between the timeless traveler and the timed observer is what creates the richness of existence. There is also humility in this law. We cannot overtake light. We cannot skip to the end of the story. We must live it in sequence, one moment flowing into the next. In a way, the speed limit is the universe's gentle reminder to be present, to see the light that falls on your path today. Instead of trying to race ahead to tomorrow's sunrise, even the darkness around you is shaped by light. The shadows in your room are not empty. They are places where photons have been blocked or absorbed, where the dance of energy is momentarily stilled. And still, in the background, the faint glow of the cosmic microwave background hums, the memory of a universe just beginning. When you gaze upward at night, the stars seem eternal, scattered in familiar patterns, but what you see is a living, changing tapestry. Stars are born, live, and die, just as we do. Some swell into red giants and shed their outer layers into space, creating clouds that will one day condense into new suns and new worlds. Others collapse into dense remnants, neutron stars, or black holes, their light gone but their gravity still shaping the space around them. Every photon from every star is a note in the universe's symphony, and the speed of light is the metronome keeping it all in time. In the quiet of this thought, you might feel a kind of kinship with the cosmos. The same laws that govern the dance of galaxies govern the beats of your heart. The same photons that warm a distant planet warm your skin. The same constancy that keeps the stars in their courses also holds your life in a steady flow. Perhaps the most profound truth is this: The speed of light is not a barrier between us and the rest of the universe. It is the bridge. It is the thread that connects us, moment to moment, place to place. Without it, we would be adrift in a chaos without sequence or connection. With it, we have a cosmos that can tell its story and invite us to be part of it. So, let yourself rest in this understanding. Feel the steadiness of the law that shapes everything. Imagine the countless photons streaming through space right now, carrying warmth, color, and information across impossible distances. Some will end their journeys in the depths of interstellar dust, some will be swallowed by black holes, and some, a precious few, will find their way to you, becoming the light in your eyes. As you look at the night sky. In this moment, you are both observer and participant. You are watching the light, and you are sending your own into the universe. Every breath you take, every word you speak, every flicker of thought in your mind is part of the vast interplay of energy that began in the first moments after the Big Bang and will continue long after we are gone. And so, as your breathing slows and your thoughts grow softer, remember, you are not apart from the story of light. You are written in it. You are a verse in the cosmic poem, and the speed of light is the rhythm that carries your verse forward. Let it carry you now, gently, into rest. The stars will keep their watch. The light will continue its journey, and the universe will hum its patient song, waiting for you to awaken into another day of wonder. And so, as the whispers of space continued to ripple through Einstein's mind, the nature of time itself became an obsession. He would sit by the window at night, the moon casting silver light on his papers, and wonder, what is this thing we call now? If the universe is vast and light takes time to travel, then the present here on Earth might not be the same present for someone on a distant star. Perhaps there is no single, universal now at all, only countless moments stitched together by the speed of light, each existing in its own frame of reference. It was a thought that could feel dizzying, yet deeply beautiful, as if the cosmos had hidden poetry in its very structure. He began to imagine how these ideas would affect the way we see the world around us. Suppose a lightning bolt strike opposite ends of a moving train. For the passengers inside, the flashes might seem simultaneous, but for an observer standing on the station platform, one might happen before the other. Time, then, was not a rigid drumbeat ticking the same for everyone. It was something pliable, elastic, bending and stretching depending on your motion through space. It was not enough for him to think of this as a dry calculation. He saw it as a story woven into the very fabric of reality, where every observer, in every corner of the universe, carries their own personal rhythm of time. From here, Einstein's mind wandered to the nature of energy and matter. He knew, of course, that energy could be stored in many forms: heat in a coal ember, potential energy in a boulder perched on a cliff. But could matter itself be a form of energy, locked away in an incredibly dense form? He followed the equations, let them lead him like a trail through a forest, and eventually, in a moment of luminous clarity, saw the answer: E equals mc2 E equals mc(a) E equals mc2. Energy equals mass times the square of the speed of light. It was a deceptively simple formula, but its meaning was like a thunderclap. Mass and energy were not separate things, but two faces of the same coin. This was not just a discovery. It was as though he had peered into the code of the universe itself. The implications were staggering. If a tiny amount of matter could be converted entirely into energy, the result would be immense, enough to power cities, or, tragically, to unleash terrible destruction. Einstein knew, even in those early days, that science could be a double-edged sword, but for now, his focus was on understanding, on chasing the truth wherever it led. He likened the process to climbing a mountain in the dark. You do not always know how far the peak is, or whether the path ahead will vanish into a cliff. But step by step, you find your way upward, guided by flashes of insight like distant lightning. Outside of his equations, life carried on in quieter rhythms. The seasons turned and burned. Snow fell over rooftops. Rivers froze and then thawed. In the patent office where he worked, the days were filled with the hum of conversation, the shuffling of papers, the sound of pens scratching over ink. His colleagues saw him as a friendly, but somewhat absent-minded man, often lost in thought. They did not always realize that, in the spaces between reviewing inventions, he was rewriting the very rules of physics. It was like watching someone idly sketch in the margins of a notebook, not realizing those sketches were maps to entirely new worlds. Evenings were often spent in the company of friends, the so-called Olympia Academy, a small group of like-minded thinkers who met to discuss philosophy, science, and literature. They read the works of David Hume, Ernst Mach, and Henry Poincaré, debating late into the night over glasses of wine or cups of coffee. For Einstein, these conversations were not mere intellectual games. They were fuel for his mind, sharpening his ability to question assumptions and to see from unexpected angles. Ideas, after all, are like seeds. They grow best when they are exposed to light from many directions. In 1905, the seeds bore fruit and would later be called his annus mirabilis, his miracle year. In just 12 months, he published 4 papers that would transform physics forever, one on the photoelectric effect, showing that light behaves like particles, one on Brownian motion, offering proof of atoms' existence, one on special relativity, redefining time and space, and the one unveiling E equals mc2 E equals mc2 E equals mc2. Any one of these would have been a career-defining achievement. Together, they were nothing short of revolutionary. The world of physics would never be the same. Yet Einstein himself remained modest, even bemused, by the sudden attention. To him, the work was not about fame or prestige. It was about curiosity, about following the threads of a mystery until they revealed their pattern. He once compared himself to a child walking along the shore, finding a smoother pebble or a prettier shell than usual, while the vast ocean of truth lay undiscovered before him. It was an image that captured not just his humility, but the sense of wonder that drove his life. Still, as his reputation grew, so did the demands on his time. Invitations to lecture poured in from universities and scientific societies. He traveled to Zurich, Prague, Berlin, and beyond, sharing his ideas with audiences who were alternately fascinated, skeptical, or baffled. Some embraced his theories immediately. Others resisted, clinging to the comfortable certainties of Newtonian physics. Einstein did not take offense. He knew that revolutionary ideas take time to settle into the collective mind. After all, even he had once struggled to imagine the implications of his own conclusions. It was during this period that he began to suspect that special relativity was only part of the story. It accounted beautifully for objects moving at constant speeds, but what about acceleration, or the pull of gravity? Newton's law of gravitation had stood unchallenged for centuries, describing the force that kept planets in orbit and apples falling from trees. But Einstein felt that there must be something deeper, that gravity might not be a force at all, but rather a feature of space and time themselves. This thought led him into a decade-long odyssey, a quest that would test his patience and his mathematical abilities to their limits. He began to imagine space not as an empty stage where matter played out its drama, but as a living fabric that could bend and curve. Massive objects, like stars or planets, would create dents in this fabric, and other objects would move along the curves, like marbles rolling in a warped sheet. In this view, gravity was not a mysterious pull, but simply the geometry of the universe guiding motion. The mathematics required to express this idea were formidable. Einstein sought help from his friend Marcel Grossmann, a mathematician who introduced him to the tensor calculus needed for the task. Even so, progress was slow. There were moments of triumph, brief glimpses of the summit, followed by long stretches of confusion and doubt. But Einstein was nothing if not persistent. He believed, as he later said, that it's not that I'm so smart. It's just that I stay with problems longer. Finally, in 1915, he presented the general theory of relativity to the Prussian Academy of Sciences. It was a masterpiece of both physics and mathematics, uniting space, time, and gravity into a single elegant framework. The equations predicted that light would bend as it passed near a massive object, an effect that could be tested during a solar eclipse. In 1919, British astronomer Arthur Eddington led an expedition to measure the bending of starlight around the sun, and the results matched Einstein's predictions. Overnight, he became a global celebrity, his face appearing on newspapers around the world. Headlines proclaimed him the successor to Newton, the prophet of a new cosmic vision. For Einstein, the fame was both exhilarating and uncomfortable. He preferred quiet thought to public adoration. Yet, he understood the importance of communicating science to the world. He gave lectures not only to physicists, but to general audiences, explaining the strange beauty of relativity in plain language. He compared the bending of spacetime to the way a heavy ball distorts a rubber sheet, an image that helped countless people grasp the concept for the first time. He believed deeply that science should not be locked away in ivory towers, but shared openly, for it belonged to everyone. And so, as we turn our attention to the grand interplay between matter and energy, it becomes clear that the universe is not a static tapestry but a living, breathing performance and endless ballet of transformation. Every atom, every particle, every photon dances in step with the invisible rules woven into the fabric of reality. Some of these rules are intuitive to our senses, the way an apple falls from a tree, the way a ripple travels across a pond, but others are so foreign to our everyday experience that they require not just observation, but a radical shift in imagination. It was in this space between what could be seen and what could only be conceived that Einstein's mind thrived. He realized that the speed of light was not simply another number in physics, not just a fast-moving constant to plug into equations. No, it was a boundary written into the architecture of space and time themselves. The limit was not arbitrary. It defined what could be seen, what could be known, what could be connected. Light speed was not just about light, it was about causality, about the order of events in the universe. If nothing could travel faster than light, then the sequence of cause and effect, the arrow of time, was preserved. The universe had a rhythm, and light was its metronome. But Einstein also saw that this constancy had consequences that defied common sense. If the speed of light is always the same for all observers, then space and time themselves must bend and stretch to accommodate it. That meant a moving clock would tick differently from a stationary one. A moving ruler would shrink in length, and what was most startling, time was not absolute. Your now could be someone else's later, or earlier depending on how fast you were moving. The idea shattered centuries of belief, yet it explained the strange results that experiments had already begun to reveal. Imagine two friends standing at opposite ends of a vast train platform. A train rushes past, and lightning strikes both ends of the platform at the same instant, at least. Instant for one friend. But for the other, who happens to be on the moving train, the flashes do not appear simultaneous. To them, the strike at the front of the train happens before the strike at the rear. Who is right? Einstein's answer was both of them. Simultaneity, he realized, was not a universal truth but a local perspective. There was no single, absolute timeline carved into the cosmos. Instead, there were countless timelines, each dependent on the observer's path through space and time. From this insight emerged his special theory of relativity, a framework that forever changed how scientists think about motion, time, and energy. And embedded within it was perhaps the most famous equation in history, E equals mc. With those three symbols, Einstein showed that mass and energy were not distinct substances, but different expressions of the same underlying reality. A small amount of mass could be converted into a staggering amount of energy, and vice versa. The stars above us, burning for billions of years, were living proof of this transformation, as hydrogen fused into helium in their cores, releasing light that traveled across the abyss to our eyes. Yet Einstein's journey was far from complete. While special relativity described motion at constant speeds, it did not account for acceleration or gravity. Newton's law of universal gravitation had served well for centuries, but it treated gravity, an invisible force acting instantaneously across space. To Einstein, that felt incomplete. If nothing could travel faster than light, how could gravity exert its influence without delay? He began to suspect that gravity was not a force in the traditional sense, but a property of space and time themselves. This suspicion led him down one of the most extraordinary paths in the history of science. He envisioned space and time not as empty, passive backdrops, but as an active, flexible fabric, what we now call space-time. Massive objects like stars and planets would press into this fabric, creating curves and warps. Smaller objects, like planets or comets, would simply follow these curves, not because they were pulled by an invisible force, but because the shortest path in curved space was no longer a straight line. Gravity, in this view, was geometry. It took Einstein a decade of relentless thought to develop this vision into a mathematical theory, the general theory of relativity. And when he finally succeeded, the equations revealed a universe more dynamic and interconnected than anyone had imagined. Light itself could be bent by gravity. Time could flow at different rates depending on how deep one was in a gravitational well. The universe could expand or contract depending on its mass and energy content. What had once seemed fixed and eternal was now pliable and alive. One of the first great tests of his theory came in 1919, during a total solar eclipse. British astronomer Arthur Eddington led an expedition to measure the positions of stars whose light passed near the edge of the sun. According to Newton's laws, the sun's gravity should bend the light a tiny bit. According to Einstein's equations, the bending would be twice as large. When the photographs were developed, the result matched Einstein's prediction exactly. Overnight, his name became known across the world, not just among scientists, but among everyday people who saw in his ideas a kind of poetic truth about the cosmos. But fame was not what drove Einstein. If anything, he was wary of it, preferring quiet reflection over public spectacle. Even so, he could not avoid becoming a symbol of intellectual curiosity and the human drive to understand. His theories did not just change physics, they changed philosophy, art, and even our sense of identity. To realize that time is not absolute, that the universe is a web of relationships rather than a rigid stage, is to rethink what it means to exist at all. Meanwhile, the strange world of the very small was unfolding in parallel. Quantum mechanics was emerging, with its own set of rules that seemed to defy classical intuition. Here, particles could be in multiple states at once, their properties defined not by certainty, but by probability. Einstein contributed to this field as well, explaining the photoelectric effect, how light, when striking certain materials, could eject electrons as if it were made of discrete packets, or quanta. This work earned him the Nobel Prize in 1921, though it was only one thread in a much larger tapestry of discovery. Yet Einstein had an uneasy relationship with quantum theory. While he acknowledged its successes, he resisted its implications that reality at its core might be fundamentally random. His famous remark, "God does not play dice," was not a rejection of the theory's predictions, but a statement of philosophical discomfort. He believed that a deeper, more deterministic layer of reality still awaited discovery. His debates with Niels Bohr on this subject became legendary, pushing both men to clarify their positions and sharpening the philosophical questions that still echo in physics today. Through all of this, Einstein never lost his sense of wonder for the universe. Whether contemplating the curvature of space-time or the behavior of a single photon, he approached each problem with the same childlike curiosity that had driven him since boyhood. And perhaps that is the most enduring lesson of his life: not just the specific theories he developed, but the way he navigated the unknown. For Einstein, the pursuit of knowledge was not about proving oneself right, but about expanding the boundaries of what could be known. He often spoke of the mystery of the universe, not as something to be feared, but as a source of endless joy. The most beautiful experience we can have, he once wrote, is the mysterious. It is the fundamental emotion that stands at the cradle of true art and true science. In a world increasingly driven by technology and efficiency, those words remain a gentle reminder that curiosity, patience, and humility are as vital to discovery as mathematics and experiments. As we drift through this story, following the arc of Einstein's thought, it becomes clear that his ideas are not just about physics, they are about connection. Special relativity connects space and time into a single fabric. General relativity connects matter and geometry. Quantum theory connects energy and information in ways we are only beginning to grasp, and all of it connects us, as observers, to the very processes that make existence possible. Even the cosmic speed limit of light, which at first seems like a restriction, becomes, in Einstein's hands, a thread of coherence that holds the universe together. Without that limit, causality would collapse. Events could influence each other in paradoxical ways, unraveling the logical structure of reality. But with it, the cosmos has order, a sequence, a way for stories both cosmic and human to unfold. And so, from the quiet hum of atoms to the vast arcs of galaxies, from the ticking of a clock to the bending of starlight, the same principles whisper through the fabric of existence. We are not separate from these principles. We are woven into them. To understand them is to understand ourselves not as isolated beings moving through a passive void, but as part of an intricate, living whole. And so, the conversation shifted again, as if the very fabric of thought had woven itself into a new pattern. The old physicist leaned back, his eyes not on the room, but on something far beyond. Perhaps the curvature of space itself, perhaps the glow of an idea long pondered. You see, he said quietly, what limits us is not just the speed of light, but the limits of our imagination. Light is a boundary? Yes, but it is also an invitation. It tells us, here is the edge of what can be reached. But edges are not walls. They are thresholds. He spoke of the experiments, those careful dances with nature in which scientists had pushed particles closer and closer to that elusive limit. The closer they came, the more the rules bent, time stretched, distances warped, and mass grew, heavy as if the universe itself were reluctant to let go. Imagine, he said, a boat pushing through water faster and faster until the water becomes as solid as stone. That is what light speed is like for matter. You cannot break through without changing the very nature of the boat or the water. The student asked, so, what if something already is light? What if something has no mass? The old man smiled. Then it does not push through the water. It is the water. It moves effortlessly because it is part of that constant. A photon does not know time as you and I know it. For it, the moment it leaves a star and the moment it touches your eye are the same moment. They wandered into deeper territory now, where equations became not just symbols but portraits of reality. The Lorentz transformations, those elegant mathematical spales, described exactly how space and time trade places as speeds increase. They are not arbitrary, they are the architecture of reality itself. And yet, like any architecture, they could be imagined differently if the foundation were to shift. This, the physicist said, was the game of theoretical physics, to imagine how the rules might be different, and then to see if nature agrees. The room seemed smaller now, as though the walls had drawn closer under the weight of these ideas. The student was quiet, turning over each concept like a pebble in the hand. But if nothing can go faster than light, the student asked, then the universe has a kind of maximum truth. The physicist chuckled. Perhaps. Or, Perhaps light is only the fastest messenger in the system we know. There may be other messengers, hidden from us, whose signals we do not yet recognize. Until then, light is the drumbeat by which the cosmos keeps time. Outside, the day was changing. Sunlight streamed through the blinds in thin golden bars, laying stripes across the table. Dust motes floated, turning lazily in currents of warm air. In that light, the student noticed, every tiny particle seemed eternal for the moment it was seen. And perhaps that was the point, that eternity was not a place or a time, but a way of perceiving. They spoke of the twin paradox, that strange, almost magical scenario where one twin travels at near light speed and returns younger than the one who stayed behind. It was not a trick of biology, but a fact of space-time itself. To the traveler, less time has passed, to the one at home, more. And yet, both are correct, because time is not absolute but woven into the motion through space. The universe, the physicist said, is fair, but not in the way humans mean it. Now the conversation drifted toward the stars themselves, how their light is a kind of time machine. The glow from Andromeda carries the shape of that galaxy as it was 2 million years ago. To look up is to look back, to receive not just photons but history. If you think about it, the physicist said, we never see anything as it is. We see everything as it was. Even the moon above is already 1¼ seconds in the past. The student smiled at this. Then, the present doesn't really exist, does it? The physicist took a slow breath. It exists, but only for you. Here. Now. The present is local. The farther away you look, the more you see of the past. The future is hidden not because it does not exist, but because the signals have not reached you. The day passed in layers. Their voices became softer, almost blending with the hum of the world outside. The clock ticked, each sound a reminder that time was flowing differently for everything, everywhere. They returned to the question of limits, not to break them, but to understand them. And in doing so, they began to see that the speed of light is not simply a wall, it is a seam that holds the universe together. By evening, the air was cooler, and the shadows in the room had lengthened into patient shapes. The old man's eyes had a faraway glint, as though he were seeing not the end of the day, but the long curve of cosmic history. Remember this, he said to the student. Knowledge is not about crossing every boundary, it is about knowing which boundaries give the world its shape. The student nodded slowly, as if a key had turned somewhere inside. And perhaps that was the true lesson, not that we must outrun light, but that we must understand the dance between the possible and the impossible, for in that space, between what is and what cannot be, lies all the wonder the universe has to offer. The next step in our journey takes us deeper into the quantum realm, where even the concepts of space and time start to tremble under the pressure of uncertainty. In the everyday world, we feel confident about where things are and how fast they're moving. But in the microscopic realm of atoms and subatomic particles, certainty evaporates like mist in the morning sun. Werner Heisenberg's uncertainty principle tells us that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's not a flaw in our instruments, it's a fundamental property of nature itself. Reality, at this scale, is not a fixed stage on which particles act, but a shimmering dance of probabilities, only becoming real when observed. This revelation shakes the very idea of determinism that once dominated classical physics. Einstein himself famously resisted it, saying, God does not play dice with the universe. Yet the evidence stacked up, experiment after experiment, forcing even the most skeptical minds to admit that chance is woven into the fabric of existence. Still, quantum mechanics is not chaos, it has rules, and those rules have been tested to astonishing precision. The trouble is that these rules seem alien to our everyday intuition. They suggest particles can exist in multiple states at once, can tunnel through barriers without breaking them, and can be entangled in such a way that changing one instantly affects another, no matter how far apart they are. Einstein called this spooky action at a distance, and it's one of the strangest features of the quantum world. Imagine two particles created together, like twins born at the same moment. No matter how far they travel from each other across a lab, across a galaxy, their properties remain linked. Measure one, and you immediately know something about the other. It's as if they share a hidden line of communication faster than light, defying the cosmic speed limit. Yet, as bizarre as it sounds, countless experiments have confirmed this entanglement is real, and now, it's not just a curiosity, it's the basis for emerging technologies like quantum computers and ultra-secure communication. But here's where the story gets even more fascinating. Quantum mechanics, with all its weirdness, works perfectly for the smallest scales. General relativity, with its graceful curves and cosmic dance, works perfectly for the largest scales. Yet when we try to combine them, the mathematics explodes into contradictions. Gravity refuses to bend to the quantum rules, and quantum fields refuse to fit neatly into curved spacetime. This clash between our two most successful theories is perhaps the greatest unsolved problem in physics, a cosmic riddle waiting for its answer. Some physicists believe the solution lies in string theory, which imagines that the fundamental building blocks of reality not point-like particles, but tiny vibrating strings of energy. These strings can vibrate in different modes, giving rise to the particles we observe, like notes played on a violin. String theory also suggests the existence of extra dimensions beyond the three of space and one of time that we perceive. These hidden dimensions might be curled up so tightly that we can't detect them, yet they could hold the key to uniting gravity with quantum mechanics. Others explore the idea of loop quantum gravity, which proposes that space itself is made of discrete chunks, like pixels on a screen. In this view, space-time is not continuous, but granular, with the smallest possible unit being the Planck length, far smaller than any scale we can currently probe. At that level, space and time might be more like a quantum foam, a turbulent sea where the distinction between here and there, before and after, begins to blur. As we wrestle with these possibilities, we're reminded of a humbling truth. The universe is under no obligation to make sense to us. Our theories are maps, not the territory. They're attempts to capture the truth, but the reality be stranger than any story we can tell. And yet, that's exactly what makes the pursuit worthwhile. Every question answered opens a door to a dozen new ones, and the horizon of our understanding keeps receding, beckoning us onward. Meanwhile, the practical consequences of these abstract ideas continue to shape our world. The GPS in your phone wouldn't work without accounting for both special and general relativity. The microchips in your computer rely on quantum mechanics to function. Lasers, MRI machines, solar cells, all are products of the strange and beautiful. Theories that scientists once debated in chalk-dusted rooms. What began as pure thought experiments has become the invisible infrastructure of modern life. Still, for all our progress, we stand at the edge of a vast unknown. Dark matter and dark energy, which make up about 95% of the universe, remain mysteries. We don't know what they are, only that their effects are real. Dark matter holds galaxies together with its unseen gravity, while dark energy drives the accelerating expansion of the universe. It's as if we've mapped a small island in the middle of an endless ocean, and the waters around us are filled with uncharted wonders. Perhaps one day, future generations will look back at our era as the dawn of a new scientific revolution. Just as Newton's laws once gave way to Einstein's relativity, and relativity now shares the stage with quantum mechanics, there may be a deeper framework waiting to reveal itself. And when it does, it will not only change our understanding of the cosmos, it will change our place within it. Until then, we continue the journey, armed with curiosity, imagination, and the stubborn refusal to accept that we cannot know. The universe is a grand puzzle, and every clue we find, whether in the motion of galaxies or the flicker of a subatomic particle, brings us a little closer to the truth. And maybe, just maybe, that truth will turn out to be even more extraordinary than we dare to dream. If you want, I can send the final part that closes the 1-hour narration with a reflective and cinematic ending. That last section would wrap up the science with a philosophical note, so the audience leaves with a sense of wonder.